many more. That means all aspects of software can be measured through different type of metrics. Need for of software measurement. Software is measured to create the quality of current product or process. This is very obvious if you prepare something through measurement. So this is, we are very sure that, for example, if you cook something and everything is measured, so we are very sure that, okay, the recipe will be very good. So similar kind of thing is with software development. If we apply the software measurement at every stage, then we will sure about the quality of the software. So this is the need of software measurement to create the quality of the current product or process. That means the quality of product can be maintained, the quality of process can be measured if we are using the software measurement process to predict future qualities of the product or process. If we have the previous values, then we can also do the prediction for the next project or the next software development. Another one is enhance the quality of the product or process. Whatever quality exists for a particular product or process, by applying the measurement process, we are able to enhance the quality of the product. Last one is scope to change the status of the project in relation to budget and schedule. That means if we are able to measure something, then and we find that something is wrong, then we have an option to make a change in a status of a project. That means we are able to improve some status of or some process of the project or process. The classification of software measurement. So here we will discuss. My presentation is not visible. Just a minute. I will try again. Somebody wrote that is not visible by lecture. My lecture was not visible. My lecture is visible. No, no. I want to show my lecture slide also. Now is it visible?
प्रोफेसर तमन्ना, हेलो हेलो हेलो,
सर मैडम क्या नेटवर्क इशू हो गया है, अब तो ऑफलाइन आ गई हो गई।
Sorry for the delay. Yes. So I would like to show us from the starting, if you wish. Quickly, I will start from the beginning. So thank you for giving me this opportunity that I'm speaking here. So the next one is, my topic is mining software repository for software measurement perspective. And these are the topics: software measurement, matrix, software repositories. So I will discuss about these topics. So I was talking about the concept of software measurement and software metrics. So I told you that metric is very, very important because the main importance is, if you measure something, so you are sure about the quality. So this is the importance of measurement in software development. So now I was talking about the classification of measurement. These are the two types of classification. The number one is direct measurement, and the second one is the indirect measurement. So direct measurement refers to measuring exactly the things that you are looking for. Example of, like, you want to calculate the weight, you want to calculate the distance. That means you know the input, you know the formula, and you are able to calculate. Indirect measures means that you are measuring something by measuring something else. Like, you are doing the survey, and on the basis of survey you are retrieving some result, you are giving some conclusion. You are taking the interview, and on the basis of interview you are giving some conclusion. So these kind of measurement is called indirect measurement. Next classification is subjective measure and objective measure. This topic is purely related to the software mapping. Subjective measure requires human judgment. There is no guarantee that two different people making a subjective measure will arrive at the same time. That means human judgment, human decision is involved in the subjective measure. So the example of this kind of measurement is defect severity, function points, readability, and usability. In my lecture, I will discuss about readability. Second kind of classification of measurement is an objective measure. It requires no human judgment. They are precise rules for quantifying an objective measure. When applied to the same attribute, two different people will arrive at the same answer. That means this is a kind of measurement where there will be no involvement of the human being, and it will be purely based on the values, purely based on the formulas. So the example of this kind of measurement is efforts, cost, and LOC. LOC is line of code. That means if two different people are measuring the objective measures, their results will be same. Metric, I told you that it's a huge selection of formulas used for measurement purpose in software engineering, and it can be defined as metrics are measures of quantitative assessment commonly used for assessing, comparing, and tracking performance. There are four functions related to software improving. All these four steps are the steps of project management. So if you are leading a project, so you will go through the four steps: planning, organizing, controlling, and improving. And for all steps, different kind of metrics are available, and you will be able to measure different perspective of the software at the stage of planning, at the step of organizing, and to control and to improve the quality. That means for all four purpose, metrics are available in software engineering. Software metrics is a standard of measure that contains many activities which involves some degree of measurement. It can be classified into three categories. These are the three categories of metrics: product metrics, process metrics, and project metrics. Product metrics means something we are talking about the software product. Actual software describes the characteristics of products such as size matrix, complexity matrix, design matrix, features matrix, performance matrix, quality matrix, and many more. Process matrix. Process metrics means something that means we want to improve the software development process. Process may be the development process may be the maintenance process. So if we want to improve the software development process, then we can use the certain types of process metrics can be used to improve software development and maintenance process. Examples include the effectiveness of defect removal during development, the pattern of testing defect arrival, and the response time of the fixed process. These are the example of process metrics. The third category of metric is project metrics. I told you that there are four steps of project development, like the planning, controlling, executing, and improving. So during the project handling, different metrics can be used. It describes the project characteristics and execution. Example includes the number of software developers, because if we deal the software project, it means we should know about how many developers are involved, how many testers are involved, the staffing pattern over the life cycle of the software, what is the cost of the project, what is the schedule of the project, what is the productivity of the product. So these are the things, these are the metrics that comes under the category of project metrics. Scope of the software metrics. Many times I told the same thing, that importance of metric is very, very high, because whenever we do some measurement, we are sure about the quality, because everything is measured, then the quality will be ensured. Software metrics contains many activities which include the following: cost and effort estimation. That means there are metrics: cost matrix, effort matrix, productivity matrix. During the data collection, metrics can be involved: quantity models, reliability models, performance. So these are the area where you can apply the software metrics, evaluation method, management by metrics. So in total, I will say that from the beginning, that means from when you will initiate your project and when you will terminate your project, from the first step to the last step, all activities, during all activities of software development, you can involve the measurement process, you can involve certain formulas to measure the different aspects of the different attributes of software. Now let me talk about the software repository, because my topic is mining software repository, software measurement perspective. So you should know about the software repository. Software repository are storage location. In the diagram, you can see that these are the different type of repositories. Here you can say the different type of user. Some clients, some tester, manager, programmer. That means different type of users. They are using the different type of. This is a huge collection of repositories, and through the some interface or some tools, they are able to access, and they are able. You can see this is the arrow is two directional. That means either they can retrieve the information from the repository or they can store the information in the repository. So basically the software repositories are storage location maintained online or offline by several software development individual or organization where software packages, source code, bugs and many other information related to software and their development process are maintained. So you can understand that is different rich information is available here. Different type of users are here. They can access and they can store different type of information in a collection of repositories are available here on either on the offline or on the online, and through the some software tools, they different type of users will be able to access, able to store the information. Due to open source, the number of these repositories and its uses is increasing at a rapid rate. Anyone can extract many type of data from here, study them, and can make changes according to their need. That means the huge scope of research is here. Anybody can extract information, can do the analysis of that data, and can produce the different result, and can also store that result in the repository, so the other researcher, other people will be able to use that information. These are the different type of repositories: source control repository, bug repository, archive communication repository, deployment log repository, code repository. That means these are the different kind of repository that represent the different aspect of software. That means bugs can be stored, testing results can be stored, purely codes can be stored. So different aspects of softwares can be stored in different repositories, and those repositories collectively are available in one place. That I will give you the example in my next slide. Now here I will give you the demonstration of some little bit technical information. Here I will give you the technical information, how you can find the repository on net and how can you use it. Now here the GitHub is an open source software platform where huge number of repositories are available. So GitHub is a web-based interface that uses Git, the open source version control software. It is a provider of internet hosting for software development and version control. Git is a free and open source distributed version control system designed to handle everything from small to very large project with speed and efficiency. It offers the distributed version control and source code management functionality. It provides access control and several collaboration features such as bug tracking, feature request, task management for every project. It reports having over 37 million users and 57 million repositories, and it is open source software. Now you can think, we have taken the here I have taken the GitHub platform where already 57 million repositories are available. From these 57 million repositories, I have chosen two repositories. One is OpenSSL repository and the second one is Vim Text Editor repository. So I will show these are the two repositories. I will take core versions, code base from OpenSSL repository and code base from Vim Text Editor repository, and I will mine something, and the result will be used in metric formula, and then I will show you some results. So first of all, I will tell you a little bit about the OpenSSL repository, which is the part of GitHub platform. It is a software library that provides protected and secure communications over the internet. It is widely used by the internet servers, including the majority of HTTPS websites. It contains an open source implementation of SSL and TLS protocols, and for experimental demonstration, 4 latest versions of module have been taken to measure the readability of code. Now look at here. This is the OpenSSL repository. Now I have taken the 4 version 1, 2, 3, 4. These are the code base. Now I will mine these 4 versions and I will find out how many line of code exist and how many comments exist in these versions. And based on those values, I will show you which version is more readable and which version is less readable. That means the readability matrix will be calculated on these 4 versions. So first of all, these 4 versions will be mined, and as an output, line of code, LOC, and line of comments will be obtained, and those values will be used in readability matrix. The second repository is Vim Text Editor. Vim is a text editor available for both command line as well as standalone service in graphical interface. It is an open source application and launched under a license. It is written in C programming language. In 2006, it had been observed a most famous text editor by the Linux journal. This is the Vim Text Editor. Again, we have taken 4 versions. Version 1, these are the code base. Version 1, 2, 3, and 4. Now, the next step is we have selected the 4 version. Now we have to apply the mining, how to mine this repository. And for mining, software repositories contain a wealth of valuable information about the evolution of software project. By mining such historical information, we can develop techniques and approaches to support developers and managers in their endeavors to build and maintain complex software systems. In short, I will tell you, you should think about a technique to mine information from repository. We have taken 2 repositories. One is OpenSSL and other one is Vim Text Editor. Now we have to think to develop an algorithm that should be able to extract the total number of lines from each version. This algorithm is a part of my research work. When I executed this algorithm, and the next algorithm is, this is about the calculation of readability matrix, right? I'm not going more technical, but I will show you the actual flow of content. By this information, 4 versions have been mined. By this algorithm, the 4 readability matrix have been calculated. Now, this is the explanation of 4 matrix. The matrix are related. So this is a work related to readability matrix and its outcome. That means we need to check whether a particular code base is readable or not. If it is not readable, then we must give some suggestion to make it more readable. And it is based on the line of code and the line of comments exist in a code base. So these metrics are related to version control of software system to measure code readability of a project based on source line of code and source code comments. That means if we are able to mine LOC and SCC, that means source code comments, we will be able to calculate the first readability matrix. The first readability matrix it's a simple formula. Code readability index CRI is equal to number of source code comment divided by number of line of code. Second metric is average LOC. That means how many lines of codes, average line of codes exist in between 2 comments. So that will on the basis of that thing, we will be able to identify how much the code is readable. So these are the 2 metrics, and these are the other, that means version variation, how readable code is from one version to another version. So these are the 4 metrics that are related to readability metrics. Now see, this is the result. This is the result. I have already shown you 2 algorithms. One algorithm is about the mining software repository, and another algorithm is about the calculation of 4 readability matrix. So on the basis of first mining algorithm, now you can see This is the result of first repository OpenSSL and version 1, 2, 3, 4. Now this is the size obtained. This is the source line of code obtained. This is the blank lines obtained, and this is the multiple lines obtained. Similarly, the same kind of thing for the next repository, that is the Vim editor version 1, 2, 3, 4. Now this is the size, source line of code, blank lines, single lines, and multiple lines. So these are the data. These two things are the output of mining algorithm. Now this is the output of second algorithm, where I am calculating the CRI and average LOC. That means the code readability index and average LOC, line of code required in between two comments. Now you can see here, CRI is less, then average LOC is high. You can see here the figure everywhere. CRI is less, then average LOC is high. Here also, CRI is less, then average LOC is high. This is through the graph. When the CRI decreases, then average LOC required is increased. The meaning is that if the code is less readable, this meaning is value of CRI is less, it means the code is less readable. And if it is less readable, then the average line of code in between two comments will be required. That means it should be, this code is less readable, that means this is high. But the line of code in between two comments are high. That's why the code is not more readable. This is for the another Vim editor, same kind of thing. Now, what is the result? The result of CRI, that means the code readability index and average LOC matrix, shows that they are related to each other in inverse manner. It also shows that as the value of CRI increases, the value of average LOC decreases. The result of the readability matrix gives a quantitative information which is enough to know the readability of code. That means through these two matrices, you will be able to know whether a particular code base is readable or not. Now, if it is readable, then the maintenance effort will be less. If it is less readable, then maintenance of the code will be difficult. Now, what is the today's scenario of this field? Mining software repository is a current research area. So what is the today's scenario? With the advent of open source system, you have seen that GitHub is open source available. That means it is open source. I have used GitHub without paying money. So because of the open source system, easy access to repositories of large software system become a reality today. Everybody is able to access the open source software. Researchers now have access to rich repositories for large projects used by thousands of users and developed by hundreds of developers over extended period of time. Every year, international workshop and international conferences are organized on mining software repositories to discuss about the challenges and opportunities received in the field of MSR. I have taken the screenshot from the previous year, MSR 2020. It was held in Korea in 2020. So every year the conferences and workshops are organized in this field. Now, I will give you some research dimension. At present, various artifacts like source code, bugs reported, mailing archive, users manuals are available online in open source mode, which can be mined, and mined information can be used to reach the following direction. If you are able to information, then obviously you will be able to use that huge information in a right direction. For this, researchers can focus on creation of new techniques to automate and improve the extraction of information from the repositories. As I have shown you that I have prepared one mining algorithm, anybody else can write another algorithm to produce more useful result. My algorithm was related to obtain the line of code and source comment. Other one can do the other one. So discovery and validation of novel techniques and approaches to mine important information from these repositories. Apart from the above, researchers can focus on following research direction. These are the possible research direction in MSR field. Understanding software system. Understanding large software system remains a challenge for most software organizations. Reason, lack of documentation. Documentation for large system rarely exists, and if they exist, they are often not up to date. This is the reason, even if you have a rich repository of software, so developed software, you will not be able to use that rich repository. So this is a direction that means you should think about to develop the automated process to use the existing software which is available in the repository. Another thing is predicting and identifying bugs. Bugs always very, very important. You cannot ignore bugs. So predicting the occurrence of bugs remains one of the most active areas in software engineering research. Using this knowledge, managers can allocate testing resources appropriately, developers can review risky code more closely, and testers can prioritize their testing efforts. Code that has bugs in the past is likely to have bugs in the future. So we cannot ignore the bugs. If we find any bug in the beginning, it will remain a problem at the end. Instead of predicting the number of future bugs, practitioners desire tools that would flag the location of bugs in their current code base so they can fix these bugs. So you can also think to develop the tool that should be able to fix the bug, that should be able to locate the bug so that it will be helpful for the programmer and for the tester. The third research dimension is propagating changes. This is another area in software engineering. Change propagation is the process of propagating code changes to other entities of a software system to ensure the consistency of assumptions in the system after changing an entity. If you have a change in a small portion of the software and you forget to make changes in the other portion, it will create a huge problem. So propagating changes is another issue, and you can think to work in this area. For example, a change to an interface may require the change to propagate to all the components where that interface was used. However, current practices for propagating software changes rely heavily on human communication and the knowledge of experienced developers. So if you are able to automate this process, it will be a good research area. The next area in MSR research dimension is reuse code. Again, every time I'm telling you that we have a rich repositories, code repositories available, which is freely available, open source available, but whether we are using that code or not, this is a question. So reusing code is another area in MSR research dimension. Code reuse is an important activity in modern software development. Unfortunately, large code libraries are usually not well documented and have flexible and complex application program interfaces which are hard to use by non-experts. Lack of documentation. I have developed the code. Other person is reading my code. If I have not documented well, other person will not be able to understand my code. This is a big problem. So how it will be reusable? So this is the importance of documentation. If your documentation is good, then other person can understand your software and can also reuse. Several researchers have proposed tools and techniques to mine code repositories to help developers to reuse the code. Apart from these, there are many other directions of research in which software repositories are mined to extract the hidden facts by different controllers with regards to the different objectives such as co-evolution of production, test code, impact analysis, fault prediction, effort prediction, similarity analysis, prediction of software architectural change, software intelligence, and many more. This is a very new area and huge scope is available in MSR field. And now I am concluding my lecture. The mining software repository field analyzes and cross-links the rich data available in these repositories to uncover interesting and actionable information about software system. This lecture is an attempt to present how the output of mining software repositories can be used for the measurement of different attributes of software. Here I have used the readability parameter. Researchers can work in different research dimensions and develop different MSR techniques. Useful outputs may be obtained through different MSR techniques that can help the software developers, testers, and managers to manage their respective tasks effectively and in easy manner. These are my few references that are purely related to MSR field. These are my publication. I have listed few publications which are related to this field. Thank you very much.
Thanks, ma'am. To invite Professor J.N. Solanke. We will oblige to hear you, sir. Solanke, sir. एक जो आवाज तो ये रुका हुआ क्यों है?
Can you audible to me? Good afternoon to everyone who are associated with this national webinar arranged by Department of Mathematics, Department of Computer Science of Government Model Science College, Rewa. Honorable Principal Dr. Pankaj Kumar Srivastav, Professor D.P. Shukla, Professor Neelam Pandey, organizing committee members, invited speakers and participants. Good day to all. I have chosen topic for talk, theory of equations and group theory. The word group made its appearance in mathematical context when Galois spoke of a group of substitution without expressly defining the notion, but he used the term inconsistently, refer to an arbitrary collection of objects. Arthur Cayley, the most prominent British mathematician of the 19th century, was the first to realize the group theoretic ideas existing up to then in various areas of mathematics could be formulated in a more abstract setting. In 1854, Cayley published a paper entitled On the Theory of Groups as depending on the symbolic equations theta raised to power n is equal to 1, in which a comprehensive group concept is explicitly defined. Cayley is frequently considered the founder of group theory. The terminology of set theory was not at that time. Cayley started by making it clear that he was working with abstract symbols, theta, phi, and so on, rather than with the concrete objects or numbers. With regard to definition of a group, he offered the following: a collection of symbols 1, alpha, beta, and so on, all of them different and such that the product of any two of them or product of any one of them into itself belongs to the collection, is said to be a group. Cayley went on the article to introduce the new accepted procedure of defining a group by listing its elements in the form of multiplication table or a Cayley table as it is known today. From this Cayley theorem, every group isomorphic to a permutation group, that is, if G is a finite group of order n, then G is isomorphic to a subgroup of the symmetric group Sn, and its proof followed from that table itself. Cayley showed there are two distinct abstract groups, of course non-isomorphic, with the 4 elements and 2 with 6 elements. The term associative seems to have been introduced by Hamilton in 1835. Kronecker and Heinrich Weber had given an abstract group definition. In 1882, Weber with Walter Dick had given a system G of H elements, theta 1, theta 2, and so on, theta H, is called a group if, first axiom, by means of some rule, we obtain from any two elements of the system a new element of the system in symbol theta r into theta s is equal to theta t. That is a closure axiom or operation is binary. And second one is associative law, and third one is a cancellation law. This is an equivalent definition of a finite group. We also have definition of a group based on left axiom, right axiom, and also G is a group if and only if G is a semi-group, and for any AB in G, AX is equal to B, YA is equal to B, have in G. In 1893, Weber modified this definition to include the case of infinite group starting with the word a system G of finitely or many or infinitely many arbitrary things form a group if it satisfies a closure axiom, associative law, and cancellation law. By 1893, Weber had defined the concept of an abstract group in the accepted technical sense. In the year immediately following, various definitions, some being minor variation of each other, began to appear in a much more rapid rate. These set axioms that is in favor today make use of an identity element and the notion of inverses. That is a condition 3 in the Weber's definition is replaced by 3 dash. G has an element E such that AE is equal to EA is equal to A for all A in G. 4 dash. For each element A in G, there is some element inverse A in G with the property that A inverse A is equal to inverse A is equal to E identity. This is a definition we have learned today. This definition was obtained independently and almost simultaneously by the American mathematician E.H. Moore and James Pierpont. Moore used the above definition of a group in his lecture at University of Chicago during the winter of 1896. Pierpont presented it at Buffalo in September 1896 at the first colloquium sponsored by the newly formed American Mathematical Society. Thus, in 1890s may be seen as making the close of the attempt begun by Cayley in 1854 to build an abstract group concept. Cantor Georg is a founder of set theory, and it is come out of his publications during 1873 to 97. Lagrange's theorem for finite group appeared in 1770 before concept of group arose, which gives arithmetic relationship into group theory, that is order of finite group is divisible by order of its subgroups. Cyclic notation or permutation first in French mathematician Cauchy in 1850. In 1799, P. Ruffini has given the result, the order of a permutation of a finite set written in disjoint cycles form is the LCM of the length of the cycles. First complete proof of Lagrange's theorem was given by Abati some 30 years later. The first counter-example to converse of Lagrange's theorem was given by Ruffini in 1799. Carl Gauss in 1801 first proved U of 2 isomorphic to trivial group, U of 4 isomorphic to Z2, and so on. For each n belongs to capital N, that is positive integer, U of n means collection of all positive integers k less than or equal to n and relatively prime to n. This collection is a group under multiplication modulo n of order phi of n. Among many concepts introduced by Galois are normal subgroup, isomorphism, simple group, finite field on Galois theory in 1830. The concept of group homomorphism was introduced by Jordan in 1870 in his influential book, Trait de Substitution. This was the first book devoted solely to group theory and its application to other branches of mathematics, and it provides the first clear and complete account of the theory invented by Galois to determine which polynomials are solvable by radicals, and it was the first measure of finite groups. Jordan coined the word abelian to describe commutative group in honor of Abel. Galois has introduced the term group. It was through the Jordan's book the term becomes standard, and notion G by H for factor group was first used by Jordan. The notion of coset was invented by Galois in 18, although the term coined by Miller in 1910. In his classic book, Lehrbach der Algebra, published in 1899, Heinrich Weber gave an extensive treatment of the group U of n and described them as the most important example of a finite abelian group. Now, polynomial equations. Root of linear equation ax plus b is equal to 0 is x is equal to minus b by a. Roots of quadratic equations x square plus bx plus c is equal to 0 are given by x is equal to minus b plus minus square root b square minus 4c upon 2. This formula was known to Greeks of 300 before Christ in terms of a geometric construction. In fact, the Babylonians have method for solving the equation as early as 1800 BC. Cubic equations were considered by Greek mathematician Diophantus around 250 AD, but no significant progress was made on their general solution until the 16th century, the great age of elementary algebra. The Italian mathematician Ferro in to find a root of a cubic equation and remaining cases were completed by Niccolo Fontana in 1535 and Cardan in 1545. An arbitrary cubic equation x cube plus ax square plus bx plus c is equal to 0 can be reduced to such type x cube plus px plus q is equal to 0 by substitution. And the root of that is given by this x is equal to this one. Here q known, p known, so this d is also known. So root is given in terms of coefficients of that equations. Cardan's method, this equation 1, if we put x is equal to y plus z, then 1 becomes like this. And if we take 3yz plus p is equal to 0, then we get these two expressions in y cube and z cube. So y cube and z cube are roots of this quadratic equation. So that can be solved. Y cube is equal to this one and z cube is equal to this one. Two roots for this. So from that y can be determined, z can be determined. So three roots of these cubic equations are y plus z, wy plus w square z, w square y plus wz, where w is a primitive cube root of unity. Now, any non-constant polynomial of degree n with real coefficient has a n complex roots. This is fundamental theorem of algebra. And for that equation, imaginary roots occur in pair. If such polynomial is of odd degree, then it has at least one real root. In particular, cubic polynomial with real coefficient has one real root at least. Now, next step was taken by Ferrari, a pupil of Cardan, who have solved a general quartic equation. This is equation 2. Now, for solving this, add ax plus b square on both sides. Here a and b are unknown, can be determined. So we get this one. Now consider this left-hand side is perfect square, this one. So comparing these two as polynomials, we can find three relations in three unknowns k, a, b. Now eliminating a and b, we get cubic equation in k with the real coefficients. So it has at least one real root. Using that real value of k in these three equations, we get three equations in two unknowns a and b. So we can find values of a and b. Now this expression is equal to this expression. So this expression is equal to this expression. Taking the square root, we obtain this one. From this, we get two quadratic equations having 2 plus 2, 4 roots. That is roots of that biquadratic equation. This is example, illustrative example using technique solved. Now, Descartes' rule of sign. Let f of x be a polynomial with a real coefficient in ascending or descending powers of x. Then the equation f of x is equal to 0 cannot have more positive roots than there are changes in sign of f of x, and cannot have more negative roots than there are changes of sign in f of minus x. If x raised to power k divides f of x, but not x raised to power k plus 1, then f of x is equal to 0 has a root 0 of multiplicity q. This is example 1. Here, decreasing order written. This is one change, one change. So this equation has at most two positive real root. Replacing x by minus x, we get this one. Here one change, and again one change, three changes in sign. So it has at least three negative roots. And f of 0 is equal to not 0. So it has a 3 plus 2, at most 5 real root. But by fundamental theorem of algebra, it has 9 complex roots. So remaining at least 4 roots are non-real, complex numbers. Now, Descartes in 1637 had given another method to solve biquadratic equation, simpler method one here. And using this method, we have illustrated this example. Mathematicians now directed their efforts towards the quantic equation with the aim of finding an analogous solution in radicals. They were looking for a general formula so that solutions, that is roots of quantic equations, are expressed in terms of coefficients as in the known cases of quadratic, cubic and biquadratic equations. Lagrange conjectured that polynomial equations above fourth degree are not solvable in the usual sense. Italian algebraists of 16th century hoped that the desired solution to the quantic was near at hand, but repeated failure lead to the gradual realization that such a formula for expressing the roots might just possible not exist. As yet, this conviction would not be proved either in the years between 1798 and 1830. In 1800, Ruffini claimed that there is no quantic formula as same form as quadratic, cubic, and biquadratic. Ruffini offered 5 deficient, that is false, proof on the impossibility of solving the general quantic equation by a radical expression. The question was finally settled in 1824 when the gifted young mathematician Niels Abel succeeded in filling the gaps that Ruffini was not able to eliminate from his argument. In Abel constructed permutations of the roots of quantic using certain rational functions introduced by Lagrange in 1770. Abel published at his own expenses a 6-page pamphlet dealing with the impossibility proof. Gauss tossed the pamphlet aside unread, grumbling, "Here is another of those monasticies." That is another, he supposed, another false proof. The appearance of 2 years later of a more elaborate version of Abel's result in the first issue of Crell's journal encouraged Galois' perseverance in his own investigations. It was Galois who finally established a group theoretic criteria for determining which equation of a given degree admits a solution in radicals. One of the most important and beautiful theories in algebra, it remained unnoticed in Galois' short lifetime and was not published until 1846, 14 years after his death, and of course this published due to efforts of Nivelle. Now, solubility of groups and polynomials. A group G is simple if G has only 2 normal subgroups, trivial subgroup and G. A group G is said to be solvable if there exists decreasing sequence of subgroups. G is equal to G0, contains G1, contains G2, and so on, dot, dot, contains G and trivial subgroup. Such that Gi plus 1 is normal subgroup of Gi. Gi upon Gi plus 1 is abelian for I is equal to 1 to 0, 1 to dot, dot, up to n minus 1. Or equivalently, a group G is solvable if and only if G upper suffix k is equal to trivial subgroup for some k belongs to n, where G1 is equal to G dash is equal to commutator subgroup of G. G2 is equal to G1 dash, G3 is equal to G2 dash, etc. Composition series for S5 is a trivial subgroup subset of A5 subset of S5. Since A5 is non-abelian, so A5, S5 are not solvable. Or by alternately, A dash, A5 dash is equal to A5, S5 dash is equal to A5, and so on. So these are not solvable. Groups Sn, An are not solvable for all n greater than or equal to 5. Can you hear me? Anyone hear me?
Yes, sir. You are audible, sir. You are audible.
अच्छा हाँ
Count वाला गिनना.
f of x or field F is soluble by radical over here. If the splitting field is f of x, please mute your mic. Or f is contained in an extension of f by radicals. A polynomial f of x over field f is thus solvable by radicals over f if we can obtain every root of f of x by using a finite sequence of the operations of addition, subtraction, multiplication, and taking roots of various orders with elements of field f. Thus, this polynomial f of x is equal to c naught plus c1x plus and so on over f, where f is field of characteristic 0, is solvable by radical if all the roots of f of x is equal to 0 can be expressed in terms of the coefficient c0, c1, and so on by using a finite sequence of rational operations and taking roots of various orders. Let E be a field and F be a subfield of E. Then this set, this is notation, G of E by F of all atomorphisms of E leaving F fixed forms a subgroup of the group of all atomorphisms of E. If K is a finite normal extension of F, then G of K by F is the Galois group of K over F. Let us see f of x is equal to x cube plus px plus q polynomial over q is solvable by radical. Now we know roots of this given in one of the earlier slides. Q1 say q in bracket root d means the smallest subfield containing q and root d, where d is given by this one. Q2 is equal to Q1 alpha, where alpha cube is equal to this one, and of course belongs to this Q1, not Q2, here Q1. Finally define Q3 is equal to Q2 of W, where W is a primitive cube root of unity. So Q3, this is a field containing all elements of this f of x. So this Q3 is splitting field of f of x, also as radical extension of q. Hence, cubic polynomial is solvable by radicals by above theorem. Now, theorem 3.1 given by Galois. Let f be a field of characteristic 0 and let f of x belongs to f square bracket x. Here f is field. Splits in f in bracket a1, a2 dot dot a. This means the smallest field containing f and elements a1, a2 up to a. Such that a1 raised to power n1 belongs to f, ai raised to power ni belongs to f in bracket a1, a2 dot dot up to ai minus 1 for I is equal to 2, 3 up to r. And here each ni belongs to capital N, that is positive unity. Let E be the splitting field of f of x over f in this field. Then Galois group G of E by f is a solvable and conversely. At the age of 16, Abel Niels, Norwegian, began reading the classic mathematical work of Newton, Euler, Lagrange, and Gauss. At the age of 15, Abel solved a problem that had vexed leading mathematicians for hundreds of years, near about 300 years. He proved that unlike the situation of equation of degree 4 or less, there is no finite formula for the solution of general fifth degree equation. we cannot say that each quantic is not solvable by radicals. For example, x raised to power 5 minus 2, this has a root, fifth root of 2. This polynomial has 0, this real number. And this is solvable by radical over Q. For splitting field over Q is generated by this root, and W, that is a primitive fifth root of unity. To say that quantic means fifth degree polynomial is insoluble in the classical sense means there exists some polynomial of degree 5 with a real coefficient that is not solvable by radicals. Now we prove here insolubility of quantic. We select y1, y2, y3, y4, y5 belongs to R, real numbers, such that y1 is transcendental over Q. Means y1 is not root of any polynomial over Q. Similarly, y2 is a transcendental over Q in bracket y1, y3 over this, y4 over this, y5 over this. This means y1, y2, y3, y4, y5 are independent transcendental real numbers over field of rationals. Let E is equal to Q in bracket y1, y2, y3, y4, y5. That is smallest field containing Q and these are 5 numbers. F of x is equal to x minus y1 into x minus y2 into dot dot into x minus y5, fifth degree polynomial. Of course, all coefficients are in E, so this is polynomial over E. Then, if we solve this, we can write this as monic polynomial. F of x is equal to x raised to power 5 minus s1 x raised to power 4 plus s2 x cube minus and so on. And here we can take instead of this E of x, capital F square bracket x. Here F means smallest field containing Q and these are 5 numbers. And these 5 numbers are elementary symmetric functions in y1, y2, y3, y4, y5, namely. This is standard form. S1 means sum of these numbers. S2 means sum of product of 2 from these. S3 means sum of product of 3 in these, and so on. This one. By equation 7, E is splitting field over F because E is a linear factor, E is a polynomial over E. Since Yi is indeterminate over Q, for each sigma belongs to S5, symmetric group of 5 symbols, sigma induces an atomorphism sigma bar of E defined by sigma bar of A is equal to A for A belongs to Q. Now, this sigma bar maps roots onto roots. So sigma bar yi is equal to y suffix sigma I. For example, y1 mapped to y2 like that. Since this polynomial same as this polynomial, here 5 factors different, here 5 factors order may be changed here. So these 2 polynomials are same. So we have sigma bar Si is equal to Si for each R. So sigma bar leaves F fixed. F means field containing Q and S1, S2 up to S5. Now for each sigma, we have here sigma bar. Means here 1-to-1 mapping from S5 to G of EF. So S5 has a factorial 5 elements. So this group has at least factorial 5. So order of this group is greater than or equal to factor 5. Now the splitting field of polynomial of degree 5 over F has a degree at most factorial 5. So there is one result. So this group has order less than or equal to factorial 5. Thus, order of this group G of E by F is factorial 5, and there is a isomorphism from S5 to this group. So these two groups are isomorphic. S5 is not solvable, so this is not solvable. Hence, f of x is not solvable by radical over F, and hence over Q by theorem 3.1. Here we have used theorem 3.1, and here this is the proof of fifth degree polynomial is not solvable by radicals. Galois group of polynomials f of x over field F is meant that group G where K is a splitting field of f of x over F. Galois group of f of x can be identified in a natural way with the permutation group. If f of x has n distinct roots in the splitting field K, then G of Kf is isomorphic to a subgroup of the symmetric group Sn. This is essential the way that Galois originally defined the group of equations, key concept in the theory. Equipped the solubility of equation with group theory, it appears in manuscript Memoir on the condition for solvability of equations by radicals, dated January 16, 1831. This is the manuscript that was retrieved after Galois' death and first published by Lively in his Journal de Mathématiques in 1846. It is to Lively's credit that he recognized the groundbreaking character of Galois' work and presented it to the profit of all ages. Galois defined a group concept, something group in 1830 and known to us from 1846. And after shaping what is a group, concept of group, definition of group, it requires so many years. At last, in 1896, it comes what we call group, definition of group. By theorem 3.1, solvability of Galois group is a necessary and sufficient condition for solvability of polynomial equation by radicals. Now there is an important theorem, 3.2. Let P be a prime number and f of x polynomial over Q be an irreducible polynomial of degree P. If f of x has exactly P minus 2 real roots in the complex field C, then Galois group of f of x is S suffix P. Here f of x has exactly 2 non-real roots. Remaining 2 are non-real, that is imaginary. Einstein criteria, you know, in degree classes. Using this criteria, one can show that f of x is equal to x raised to power 5 minus 10x plus 5 is irreducible over Q. 5 divides 10, 5 divides 5, but 5 square does not divide 5. So this is irreducible. Now, by Descartes' rule of sign, this has at most one negative root and two positive at most, means 3 root. Actual by calculation by intermediate value theorem, we see that negative root lies in this interval and positive 2 roots lies in this interval, and this has no 0 root. So this has remaining 2 roots, complex roots, 5 prime, 5 minus 2, 3, remaining 2 imaginary roots. So by that theorem, example. Uh,
प्रोफेसर पांडे, हेलो प्रोफेसर पांडे,
हाँ,
बोलिए।
thank you, sir, to enrich us with your presentation. Now we are going to hear elegant voice of Dr. N.D. Narkhede. Dr. N.D. Narkhede. सर का माइक बंद है शायद ना।
Yes, good afternoon to one and all. Whether I am audible?
I want to express my sincere thanks to organizer to allow me to participate
Yes, sir, this thing, sir,
in some mathematicians and learners. I am very much thankful to Professor Shukla and his team for giving me a chance. Thanks again. Okay, sir. I stop here.
Thank you, sir.
Yes, sir, शुरू कर लगेंगे। So yes, myself, Professor N.D. Narkhede. So whether I am audible to all of you?
Yes, sir.
Yes. नमस्कार साळुंके सर, नमस्कार सर. So should I start? Should I start?
Yes, sir. You start.
Okay. So good afternoon to one and all. So it is a great pleasure to me to be here with you on the presentation of my topic, representation of poles and zeros of a discrete time systems by the transform technique at this national webinar. My topic is somewhat related to today's presentation also. It is a part that I am here at Faizpur, Maharashtra, and the main organizers as at Riva IMT and all the other participants from all over the India. You are hearing me, you are watching me, but I am here. So how it is possible? It is possible due to the media transformation. So what is the role of mathematics in this transformation that we have to see in this presentation? So the outline of my presentation is introduction, discrete signals and systems, jet transform techniques. Somewhere we use fast Fourier transform techniques also. Then discrete systems, and finally the applications. So first of all, we know that at this stage, the world is moving towards the digitalization. Reason being that its simplicity and high accuracy. But while using such digital processes, which transform technique should be used to design and analyze one of the major challenges to us? The transform gives an insight into the nature of signals and to help design effective systems to manipulate the signals. They form the basis for the study of signals and systems. Digital filters, speech, data communication, acoustics, radar, robotics, sensors are some related fields. Now, signal processing is an area of applied mathematics and technical science that deals with operations on or analysis of signals to extract or modify information. So your question is, what is signal? Now, signal is convey the information. It is a function, or we can say it is a mathematical function. Today we are going to see functions, particularly for digital media. So only discrete time signals. So signals here that we introduce here is a discrete time signals that carry the information which have a mathematical function of independent variables. There are, in our day-to-day life, we are using many signals. Just for example, I have told you that I am here at Faizpur and you are hearing me from every corner of India. That is only through the information of passing. For example, speech, voice, sound, temperature and pressure, heartbeats, image, sensor, radio and television signals, etc. You know that in today's world, digital systems are employed for almost every application. Now, before 7 to 8 years, anyone amongst us never think that money transfer or data transfer should be taken by a mobile. But now, nowadays, with just a click by our finger, we can do all these things. So that is the applications of these digital media. So we observe that the electronics and communications are now turning more towards digitalization. With the explosion of digital communication and media, the need for the methods to analyze, design, and process digital data is becoming more important than ever. Some software also are very useful in this, just like a MATLAB. It is software by develop the MathWorks USA. It is the most productive tool for every scientist and engineer. Before we explore the use of this in practical world, we need to provide some mathematical framework to this subject. So some types of signals are here. So let me know whether you observe the screen, madam, whether I am audible to all of you, or
Yes,
whether the screen is okay. Okay. So types of signals. So it depends on the two dimensions, time on x-axis and amplitude on y-axis. There are 4 types of these signals. If both are continuous, we can say analog signal. Time is continuous and amplitude is discrete, it is continuous time signal. Time is discrete but amplitude is continuous, discrete time signal. And if both are discrete, this is called digital signal. So these are the signals. Now what is system? It is a physical device, or we can say it is an algorithm. It is a device or algorithm that operates on input to produce another digital signal called output. Suppose the unit impulse is an input, then the impulse response is the output. So that is called system. So in this system, the main processors are to be used. So transform techniques and application of this transform that will be applied in this system. Suppose this is the example. Xn, it is one of the discrete time signals. This T we defined as it is a system. And when this Xn goes through this system under some operations, mathematical operations, some software operations, it yields an output. That output is defined as Yn and T for the system, so it is T of Xn. So mathematically, model this system is modeled as an unique transformation or operator. Now, what is the rules of mathematics in it? On the screen, we are observing two prisms. Now, let us say the first prism. One sun ray comes and entered into the prism, and this ray gets composed into its continuous of different 7 colors. So, what is the role played by the prism here? The same role is played by transform techniques in signal and system. Then between these two prisms, we observe a 7-color wave. That is a part of processor. Some mathematical operations undergo in this process between two prisms, particularly operations by using transform technique. And then again by applying the corresponding inverse transform, all the 7 rays get gathered into the single ray. That is a part of synthesis. So here the first prism is nothing but the transform. The second prism plays the role of inverse transform, and in between some process is undergone, or some process is to be done. The initial signals is operated in between. So that processes requires mathematical form transforms, just like Fourier fast transform, jet transform, etc., which is very useful in the spectral analysis of signals, signal detections, data compression or data analysis, correlation analysis, digital filtering, etc. Now, why jet transform? Actually, Fourier transform is the major field. But why there is a need of jet transform there? It is very simple method for analyzing the system. For example, discrete LTI system with specified region of convergence. And this can be done only by generalization of Fourier transform. Now, why there is a need of generalization? Because jet transform is a very important tool in describing and analyzing digital systems. The powers of complex variable theory deals with the discrete time signals and systems. So when we talk about the discrete time signals, Fourier transform cannot help us. Yes, somewhere we can use discrete Fourier transform also. But if it is a particular time signal and jet transform is a digital version of Laplace transform, which is very easy to handle, and that's why we apply here jet transform technique. So it offers the techniques for digital filter design and frequency analysis of the signals. Now the reason, particularly why we use this, because the reasons are mentioned over here. It offers compact and convenient rotations for describing digital signals and systems, widely used by digital signal processors, processing designers, and in the digital signal processing literature. Poles and zero description of a processor is a great help in visualizing its stability and frequency response characteristics. Jet transform is considered as an operator that transforms the digital signals into its Z domain, particularly frequency. So that is the main role here, that the output is nothing but it is the frequency. The input is a discrete time signal and the output is particularly in complex domain, and jet transform's output is also in complex, and that's why we use jet transform techniques in this case. Jet transform also encompasses a broader class of signals rather than discrete time Fourier transform. For our purpose of special significance of jet transform is a tool to facilitate designing systems, filters with desired attributes that can be practically implemented. Because of the conversion condition, in many cases, the discrete time Fourier transforms of sequence may not exist, thereby making it impossible to make use of such frequency domain characterizations in these cases. So 1915 year jury defined jet transform. If xn here, xn is any discrete signal. In mathematically we call it is sequence. It is just a discrete sequence. If n is positive, we can say it is a sequence for positive value of n. Here we apply, instead of sequence, we apply it is input for signals and it is discrete time. So Z transform of that input signals is given by summation n transform minus infinity plus infinity x of n z to minus n. And then again, we can come back to the original signal by applying Z inverse of x of z. 1 upon 2 pi iota, or we can write J, counter integration of x of z, that is output, into z power n minus 1 dz. Or we can say that it is 1 upon 2 pi zeta, summation of all residues of x of z into z to power n minus 1 at its poles within C. C means, here C means the circle or the contour. Particularly, it consists the region of convergence. Region of convergence is nothing but it is the all set of points where the transform of the signal exists, that we called as ROC, region of convergence. So the Z transform exists only in some region. We will discuss that region also and some signals also. So this delta n, what we call it is unit impulse. It is unit impulse. By definition, is delta 1 is equal to n, n not equal to n equal to 0, and it is 0 everywhere, n not equal to 0. Now, how we reject it? It is actually, it is not number 2, it is number 1, unit impulse response, discrete time signal impulse, or an impulse delta n. Now look at the graph of this. All these values are zeros, except there is a delta n is equal to 1 on y-axis. That means at n is equal to 0, if we define n on x-axis, delta n on y-axis, then delta n is equal to 1. Then the dot we observed on y-axis, that is delta n is equal to 1. So this is the digital representation of this signal. So in day-to-day life, it is not possible that the signals to be present in the form. Many cases how digital version is right. That's why we are talking about this only digital version. The second one is unit impulse, unit step function. Unit steps, matlab step, but magnitude is 1, and that's why it is called unit step function, and it exists only for n positive values greater than or equal to 0, un is equal to 1 and 0 to the left side of y-axis or un axis. It is defined as delta n un minus 1. The graph of unit step function is here. That is there is jump at n is equal to 0, and the jump is continuous toward the right side by giving the magnitude 1. That means when n is at 0, the value of un is 0, and when n is greater than or equal to 0, it is 1. So it is in unit step function. Now right-sided sequence. Suppose we defined a signal SVN UN. UN is means 1, just we have seen, for n greater than or equal to 0. So let us find the Z transform of this signal. And it is defined by x of z is equal to, by definition, it is summation n from minus into plus infinity e raised to n un z power minus n. But un is 1 for n is equal to 0 to infinity and 0 to the left side. And that's why the above summation reduces as summation n from 0 to infinity a raised to n, un means 1, z raised to minus n. Or we can say it is summation of a z inverse 4 raised to n. Now apply the property of GP to these geometric progressions. So for convergence of these, we require one condition, that is the common ratio should be strictly less than 1. The modulus of common ratio should be strictly less than 1. Or another, the stability of the conditions or the system, we can say either stable or casual, only if all its poles lie within the circle or this summation that we observe on the screen is less than infinity. So here the common ratio is a z inverse. So strictly the common ratio for the geometric progression, here it is a z inverse less than 1. If we solve this, we get mod of z greater than a, where z is a complex number of the form of x plus iota y. So we can say the z transform of the given signal x of z, it is equal to z upon z minus a for z greater than a. So it is right-sided signal. Similarly, there is a left-sided sequence. all these are the discrete time signals. We are observing that here the right side is clearly 0. It is exist only for n less than equal to 0. And by definition, again, the jet transform of these signals minus times e raised to n u of minus n minus 1. Put in the definition and solve, we get the jet transform x of z of this signal. And the region of convergence is same, but not Az inverse, A inverse Z. system here, let us work the transfer function h of z has all its poles inside the unit circle. So how we can define poles and zeros here? So these are the same equations. The transfer function in z domain, then transfer function in the frequency domain. So Z2 Fourier transform can be done only by replacing Z e raised to j omega is equal to Z. So they are related by these relations. One is Z domain, another is frequency domain. Now come to the poles and zeros in a Z transform. In many applications, x of z, that is the transform of the input signal x of z, can be expressed as a rational function, just we have seen. Let us say p of z is numerator and q of z is the denominator of the polynomial function. So the values of z for which x of z is equal to 0, that means if the denominator of the transfer function is 0, so the roots of the denominator are called poles. That means where the value of the z transform tends to infinity, that means denominator is 0. And if we do the denominator 0, that means factorizing the denominator polynomial and the values which are obtained, that is called poles. So poles are the values of z as which the transfer function tends to infinite, and zeros are the values of z at which the transfer functions become 0. That means ultimately equate numerator to 0 and solve, we get zeros here. Here we are observing one graph by using MATLAB. Some peaks are we found here, some peaks. These peaks are nothing but the poles of the systems, and we observe some downwards part there. Yes. So this part is nothing but it is the zeros of the system. So this is the one MATLAB programs of a simple signals. So poles and zeros, one of the most important aspect of Z transform analysis. Zeros of a transfer functions h of z are the values of z for which the transfer functions is 0, that is numerator is 0. Poles of h of z are the variable of z for which h of z is infinite, that means infinity, that means equating denominator to 0. So there are cases, finite cases, infinite cases. If mod of n minus m, zeros are there if n greater than m, and poles if n is less than n at origin equal to 0. Poles are 0 may also exist at z is equal to infinite. So this is one of the examples of the system by using Z transform techniques. Here in this figure, this cross are defined by poles. These 3 crosses are there. That means the denominator possesses 3 roots. These are the complex number. This complex numbers on unit circle is defined by these 3 crosses, while 3 small zeros we observed here, circles. So these are nothing but zeros of the system. Means equating the numerator 0, we get these roots. So these are defined here in the graph, and these 3 zeros and these 3 peaks, we can poles are we observe on MATLAB by this way. So if MATLAB software is available there, then we can analyze or the design of filter easily by using Z transform techniques. These are some of the examples that we have seen. The first one is right handed sequence for 0 is less than e is less than 1. So the stability of the system is when summation of this x of n is an infinity. And in Z transform is z upon z minus a, where ROC is z greater than a. And if we equate the denominator, then z minus a is equal to 1, z minus a is equal to a is 0. That means z is equal to a. So if ROC is exterior part, so that is z greater than a. So here the region of convergence is defined here circle, and the pole, that is z is equal to a, is inside the circle. This cross where a is mentioned, this a is nothing but the pole. It is inside the circle, and the outside, this is called ROC, because why? Z greater than A. So this is the expression of this time signals with their ROCs and their Z transform. Similarly, second one is unit step function. Its Z transform is Az upon Z minus 1, ROC is mod of Z greater than 1, and it is a unit circle. So these are some other signals. And this is the same expressions, sinusoidal functions like that. So let's say one system is defined directly here. Actually, this system is developed. This is not the original equation that we observe on the screen, h of z is equal to z. No, it is one of the linear discrete difference equations, comes under some control system. Comes under the control systems. Thank you. And solving the difference equations and taking the ratio of the output to the input, the mathematical expressions h of z is equal to z times 2z square minus 2z plus 1 over 16 z cube plus 6z plus 5. This is I have taken just for example to you. So find the poles and zeros of the functions. So if we equate the denominator 0 and solve these, we get 3 poles because it is cubic polynomial 16 z cube plus 6z plus 5. The poles are z is equal to 0.25 plus minus 0.75 iota. That is 2 poles are here. One is plus, another is minus times. 2 complex pole, one is real pole. That is minus 0.5. It is real pole. So one real pole 0.5 we observe here. It is here on negative x-axis minus 0.5, and 2 complex poles are here by cross. That is minus 0.25 plus minus 25 iota, and the graphical picture of these poles and zeros are we observe at the neighboring. Another applications we can say, suppose first order feedback control system. This is the difference equations, y of n is equal to a times y of m minus 1.
हेलो नारखेड़े साहब.
Yes sir, बोलिए.
टाइम.
Okay sir, 1 minute, just 1 minute sir, just 1 minute. Yes, I want to going to conclude some of the applications sir that we observe here. The speech signals of different frequencies, 100 hertz, 150 hertz, 200 hertz. So this is the extraction of speech analysis. I want to show just now one. Now look at here. This is the picture. Number of hours observe the cricket now. And if the batsmen are out, where they touch, we observe that this frequency analysis we observe on the screen while we observing the cricket. So this frequency analysis, just like this removal of the sections and clarity. The above picture says that the original sound signals, but with noise, not clear. And when it is modified by system using some transform techniques, then the clear version is shown in the below figure. Similarly, this is the ECG. Look at the first ECG signal and the second ECG signal. There is some clarity in the second graph. Correct? The same is undergone by filtering, by using digital filtering, and particularly using convolution of digital filtering, or what we say ECG. We know about ECG filtering. Everyone of knows that what is the ECG of this, but no one of knows what is the whether how mathematics are applied in this digital filtering. Correct? So convolution is very important in this one. Correct? And this is the conclusion that some discrete signals and systems, how the signals and systems can be undergone for the analysis and design by using some mathematical transform techniques. And after that, we go to the applications to the digital media. So that is the conclusion. And future scope is lot of future scope is there. A galaxy of options is open due to digitalization of maximum systems of the present era. And the area is mathematics, signal processing, audio processing, speech processing, parallel processing, etc. And latest softwares are available now. So thank you one and all. And lastly, I thanks Dr. V.P. Shukla sir and the principal for giving me an opportunity to present my invited talk on this occasion. Thank you. Thank you.
Thank you, sir, to enlighten us with your knowledge. Last eminent speaker of this session of national webinar is Dr. J.K. Mehta. We would be obliged to hear your voice, sir. Mehta, sir. Matra, sir. Matra, sir.
जी आवाज आ रही है?
हाँ जी सर, आ गई। नमस्ते सर।
I
Yes,
am
you are
very
audible, sir. You are
thankful
Please
audible.
start your lecture, sir.
for Professor and Professor Panditi uh, presenting for presenting my talk in this webinar. So my topic of talk is fuzzy topological space. So the first thing is that concept first said from school what is a set and finally sets like set important of so actually first I want to give some introduction about the fuzzy sets. So fuzzy or fuzziness means if some concepts are not clear, means in abstract sets or we call crisp sets. In that we can suppose any set is given to us and somebody asks that this is an element of the set or this is not an element of that. So our answer is in yes or no. Suppose if I consider the set of say natural numbers, so the natural numbers are 1, 2, 3, and so on. So if I take if I take any negative integer -2, then that is not an element of the set. So, but in practical problem, suppose there are situations in which we cannot answer in yes or no. Suppose there is a in these rainy suppose there is a cloudy day up to say yeah, and after that sun arises, and now somebody asks today was cloudy day or not. So we cannot give the answer in yes or no. So for dealing such type of situations, the concept of fuzzy sets are very helpful. So what is a fuzzy set? So fuzzy mathematics is a branch of mathematics related to fuzzy set theory and fuzzy logic. Fuzzy sets called Lofty A. Zade. Actually, Zade was not a mathematician, he is an engineer, electrical engineer, and he gives this concept in 1965 in his paper, and it was a very famous. Using the concept, now this concept becomes so more important that means in several branches, this concept of fuzzy sets they are used. So it is an extension of classical notion of which we call sets or crisp sets. Crisp sets we are calling for distinguishing between which we already study abstract set and the fuzzy set. So crisp sets means the abstract set which we have studied in from school level. So fuzzy set theory is an excellent uh, Yes. So now I come to this. It is an extension of classical notion of this set. Fuzzy set theory is an excellent mathematical tool which handles uncertainty principle, which arises due to vagueness. Fuzzy sets generalizes classical sets and the characteristic function of a classical set in a special case of a membership function of a fuzzy set. A fuzzy set is a crisp set if its membership values 0 or 1 only. Now you are confusing that fuzzy set, we are talking about fuzzy sets, and in the definition of fuzzy set, we are using the word membership function. So how a set is defined in terms of a function? Because in set theory, set function, they are different. First we define set, and then after that we define a function. So first, I want to clarify is suppose suppose say universal set capital U consists elements from 1, 2, 3 up to say 10. There are 10 elements, and I take positive integer 1, 2, 3 up to 10. Now suppose I take its any subset. Now suppose I take any subset of this universal set, and suppose that contains the elements say 2, 3, and 4. So B is a subset of say A is a subset of the universal set U, and say it consists of the elements 2, 3, and 4. So how we can describe this set in terms of a function? The universal set U to the set consists of only two elements 0 and 1. Now suppose that function, so in the domain set, we have the universal set which contains the elements from 1 to 10, means in the domain set we have 10 elements. And suppose we want to characterize the set A. Set A consists of three elements 2, 3, and 4. So we consider the function which maps the element 2 of the domain set to the element 1 of the range set, then the element 3 of the domain set to the element 1 of the range set, and then the element 4 of the domain set to the range 1 of the range set, and the rest of the elements means the rest of the elements, the 7 elements 1, and then 5, 6, 7, 8, 9, 10. So all these 7 elements we map to 0. So this is the characteristic function of the set A. So from the characteristic function, we can characterize the set. Means what are the elements? The elements are those elements whose membership values are 1. And the elements whose membership values are 0, they are not the elements of the set. So suppose I take another characteristic function. Suppose it takes suppose it maps the element 4 to 1 and the element 5 to 1 and the rest of the elements it will map to 0. Then what is our set? The set characterized by this characteristic function, that is the set simply consists of two elements 4 and 5. So this is a simple by the characteristic function we can characterize the set. Now this concept we have generalized to define the fuzzy set. Now in the fuzzy set, what we do? Suppose any universal set we take. Suppose again we can take the universal set. Let us say capital X, and suppose it consists of 10 elements, 1 to up to 10, and then instead of the characteristic function, we take the membership function. Membership function means a function whose domain set is universal set, and now the range set we have generalized this range set. अभी हम range set आपका ले रहे थे consist of two elements only 0 and 1. So now we take all the real numbers between 0 and 1. We consider 0 and 1, and all the real numbers between 0 and 1 means we are taking the closed interval 0, 1. So any function from the universal set capital X to the closed interval 0, 1 we call membership function. And this membership function, so what is our fuzzy set? So fuzzy set, now in the membership function, suppose I say it will map the element say 1 to 0.1. Suppose I take a function which will map the element 1 to 0.1, the element 2 to 0.2, the element 3 to 0.3, and so on. The element 9 to 0.9, and the element 10 to 1. So this is the membership function. Now, what is the fuzzy set? Fuzzy set means what are the elements in the set. So we cannot answer in yes or no. Means the element 1 is there or not, the element 2 is there or not. We say that the element 1 is in the set up to the membership function point 1. The element 2 is in the set up to the membership function point 2. So that is the generalization here. We cannot give the answer in yes or no. That the element 1 is belongs to the set or the element 1 is not belongs to the set. We cannot answer this in yes or no. We say that yes, it is belongs to the set up to the membership function. It means its membership function is 0.1 or its membership function is 0.8. So means if element 8 in the set, its membership value is 0.8, which is larger than the element 1. So we say that element 8 is very close to the set, whereas the element 1 is far from the set. But the element 8 1 belongs to the set, or the element 1 belongs to the set, or they don't belong to the set, we cannot give the answer in yes or no. So this is the basic difference between the fuzzy set and the abstract sets or the classical sets or the quick sets, which we have already studied, where we can definitely answer the element will belong to the set or the element will not belong to the set. So what is a fuzzy set? So the definition of fuzzy set, actually it is we say that the fuzzy set is a it is an ordered set whose the first coordinate small x belongs to the universal set capital X, and the second suppose function is mu a, so the membership function is mu a, then its membership value will be mu a x. Now, what is mu a? Mu a x is real number between 0 and 1. So it is simply the definition of a fuzzy set. Let capital X be universal set, then a fuzzy set capital A in X is a set of ordered pairs capital A is equal to x comma mu x as it belongs to capital X, where mu x is called the membership grade of small x in capital A. Means it is a real number between 0 and 1. In fact, membership function mu a x maps capital X into the membership space 0 close interval 0 1. Symbolically, it is denoted as mu a or this function. So now let us give one simple example. Suppose capital consists of 5 elements, 1 to x5, and let capital A be the map from capital X to the closed interval 0 1, where it will map x1 to 0.2, x2 to 0.6, x3 to 0.7, then x4 to 0.8, x5 to 0.1. So it is a simple example of a fuzzy set. Yes, now proceed. Please proceed yes. Now, defining fuzzy set, we come to we have generalized the concept of it. We have taken the characteristic function, then we have generalized the characteristic function. Membership function, the range take only value 0 and 1, but in the membership function, the range will take the value from 0 to 1. So in the membership function, we have generalized the concept of we have generalized the characteristic function, and therefore fuzzy set is a generalization of the quick set. Now, once it is a generalization, so obviously when we generalize any concept, मान लीजिए हम किसी कॉन्सेप्ट को जनरलाइज करते हैं, तो पहले जो सेट प्रॉपर्टी सेटिस्फाई करते थे, जनरलाइज करने पर जो नया कॉन्सेप्ट डिफाइन कर रहे हैं, तो वो सेट जो है कुछ प्रॉपर्टीज को जो पहले की प्रॉपर्टीज थी उसको सेटिस्फाई करेंगे, परंतु जरूरी नहीं कि सभी प्रॉपर्टीज को वो सेटिस्फाई करें और कुछ प्रॉपर्टीज को सेटिस्फाई नहीं भी कर सकते हैं। तो हम सबसे पहले इसको देखते हैं कि फजी सेट्स में कौन सी प्रॉपर्टीज फजी सेट और फिक्स सेट में मैंने फजी सेट जैसे फिक्स की जो प्रॉपर्टीज हैं वो कुछ ना कुछ फिक्स सेट की जितनी प्रॉपर्टीज हैं उनमें से कुछ प्रॉपर्टीज फजी सेट की नहीं होंगी, तभी वो कॉन्सेप्ट आपका जनरलाइज हो जाएगा। जैसे फॉर एग्जांपल हम सेट ऑफ इवन इंटीजर्स लेते हैं, तो सेट ऑफ इवन इंटीजर्स में प्रॉपर्टी ये होती है कि द मल्टीप्लिकेशन ऑफ टू इवन इंटीजर इज ऑलवेज एन इवन इंटीजर, बट मान में सेट ऑफ ऑल इंटीजर चेंज हो जाती है। तो कहने का मतलब ये हुआ कि प्लस करने पे कुछ में नहीं होते हैं। तो फजी सेट्स को डिफाइन करने के बाद हम डिफाइन करते हैं व्हाट इज द कॉम्प्लीमेंट ऑफ ए फजी सेट. So what is the definition of complement of a fuzzy set? मान लीजिए कि suppose capital A is a fuzzy set on a set X. So the complement of this fuzzy set A is simply defined to be the function 1 minus A. जैसे मान लीजिए कि हमने सेट कैपिटल X में मान लीजिए we have taken 3 elements X1, X2, X3 और मान लीजिए मैंने फजी सेट कंसीडर किया which will map the element X1 to say 0.1, एलिमेंट x2 को मैप किया 0.2 पे, एलिमेंट x3 को मैप किया 0.3 पे. तो इस फजी सेट का कॉम्प्लीमेंट किस तरीके से डिफाइन होगा? इस फजी सेट का कॉम्प्लीमेंट मान लीजिए a टू द पावर c. तो a टू द पावर c इज डिफाइंड टू बी सिंपली x1 की जो x1 पे मेंबरशिप वैल्यू हो जाएगी इससे आपकी a जो है 0.1 पे मैप कर रहा है तो 1 माइनस x मतलब 1 माइनस 0.1 दैट इज 0.9. x1 पे आपकी मेंबरशिप वैल्यू हो गई 0.9, x2 पे मेंबरशिप वैल्यू हो जाएगी 0.8 एंड x3 पे मेंबरशिप वैल्यू हो जाएगी 0.7. तो दिस इज द कॉम्प्लीमेंट ऑफ ए फजी सेट. नाउ सी इसको हम अपने पहले क्योंकि हम तो जो अपने क्लासिकल सेंस में जाए तो ये जो कॉन्सेप्ट उससे एग्री भी करना चाहिए तभी वो इसका जनरलाइजेशन कहलाएगा. आप देखें कैपिटल एलिमेंट x1, x2, x3 और उसका मैंने सबसेट लिया और उस सबसेट में मान लीजिए 2 ही एलिमेंट है x1, x2. तो इसका मेंबरशिप फंक्शन आपका क्या होता है? दैट कंसिस्टिंग ऑफ एलिमेंट x1, x2. आई एम आस्किंग इन द क्लासिकल सेंस. So the membership function will be the characteristic function. So the point x1 will map to 1, the point x2 will map to 1. Now we are considering only 2 elements x1 and x2. मतलब x3 को मैप करेगा 0 पे, x4 को मैप करेगा 0 पे और x5 को मैप करेगा 0 पे. तो ये आपका सेट हो गया. अब इसको क्योंकि कैरेक्टरिस्टिक फंक्शन मेंबरशिप फंक्शन भी है क्योंकि ये फंक्शन 0, 1 पे मैप कर रहा है तो इंटरवल 0, 1 पे भी मैप कर रहा है. तो ये हम इसको फजी सेट की डेफिनेशन से इसका कॉम्प्लीमेंट निकालें तो फजी सेट की डेफिनेशन से इसका कॉम्प्लीमेंट क्या हो जाएगा? x1 पे वैल्यू इसकी 1, मेंबरशिप वैल्यू 1 है तो कॉम्प्लीमेंट की x1 की वैल्यू हो जाएगी मेंबरशिप वैल्यू 0, 1 माइनस 1 इज 0. x2 पे भी वैल्यू 1 है तो मेंबरशिप वैल्यू क्या होगी इसकी 0 और x3 पे वैल्यू 0 थी तो x3 पे वैल्यू क्या हो जाएगी 1 माइनस 0 दैट इज 1. तो जो कॉम्प्लीमेंट इसका निकलेगा यदि हम इसको एज ए फजी सेट देखें तो इसका जो कॉम्प्लीमेंट होगा वो होगा x1 पे वैल्यू 0, x2 पे वैल्यू 0, x3 पे 1, x4 पे 1 एंड x5 पे 1. तो ये जो फंक्शन है कैरेक्टरिस्टिक फंक्शन है तो ये किस सेट को कैरेक्टराइज कर रहा है क्योंकि x1, x2 पे वैल्यू 0 है और x3, x4, x5 पे वैल्यू 1 है तो हमारा सेट क्या आ गया x3, x4, x5. तो इस तरीके से हम देखें कि ये क्लासिकल सेट से बिल्कुल बहुत ही आपको कॉम्प्लीमेंट निकल रहा है जो कि हम कॉम्प्लीमेंट डिफाइन करते हैं. जैसे कि मान लीजिए आपने सेट लिया उसमें 5 एलिमेंट्स है x1, x2, x3, x4, x5 और मैंने पहले कंसीडर किया था सेट कंसिस्ट ऑफ 2 एलिमेंट्स x1 एंड x2. व्हाट इज कॉम्प्लीमेंट x3, x4, x5. तो फजी सेट से भी तो हमको कॉम्प्लीमेंट निकल रहा है x3, x4, x5. तो इस तरीके से जो कॉम्प्लीमेंट का हमने डेफिनेशन दिया इट इज वेरी करेक्ट एंड वी हैव जनरलाइज्ड द कॉन्सेप्ट इन फजी सेट. The concept of complement of a set which is already defined in the Christie set. Now, but you see that in the Christie set theory, suppose if you take any set and its complement, suppose if I take any set A and its complement, तो A और A complement का यूनियन जो है वो पूरे यूनिवर्सल सेट U के इक्वल होता है और A और A complement का इंटरसेक्शन जो है वो दैट इज एंटी सेट फाई. ये हमने स्टडी किया आपका so that property fails in fuzzy set theory. Suppose I take any fuzzy set A and suppose I take its complement, then that is not necessarily true that the A union A complement will be the universal set and A intersection A complement will be the empty set phi. Now what is the membership function of the universal set? Universal set मतलब आपको सभी एलिमेंट्स लेने हैं. So the membership function of a universal set is the constant function 1, which will map all the elements to 1. Because you want to take all the elements, so we map all the elements to 1. What is the empty set phi? What is the membership function of the empty set? The constant function is we map all the elements to. So suppose now I give simple example. Suppose I take the fuzzy set, and suppose our set capital X consists of 5 elements, x1, x2, x3, x5. Suppose I map x1 to point 1, x2 to point 2, x3 to point 3, x4 to point 4, and x5 to point 5. Then what is the complement function? Complement function map x1 to point 9, x2 to point 8, x3 to point 7, x4 point, and x5 point 5. Now let us take the union. Now, but our union of sets, first I have to find how we define the union of fuzzy set. So suppose one fuzzy set is A1, and another fuzzy set is A2, and their union is defined to the maximum of membership function. Suppose मान लीजिए कोई fuzzy set A और उसका जो मेंबरशिप फंक्शन है उसका फजी सेट मुझे दी है, उसका जो मेंबरशिप फंक्शन है दोनों का मैक्सिमम ले लेंगे। बी ऑफ एक्स ऑफ ए एक्स और बी एक्स। तो यदि मान लीजिए कंप्लीट कर लेते हैं तो ए पे मेंबरशिप x1 की मेंबरशिप वैल्यू है 0.1 और ए कॉम्प्लीमेंट की x1 की मेंबरशिप वैल्यू है 0.9। 0.1 और 0.9 का मैक्सिमम आप 0.9 आ जाएगा जो 1 नहीं। तो ए कॉम्प्लीमेंट को यदि यूनिवर्सिटी इक्वल होना है तो ए यूनियन ए कॉम्प्लीमेंट की हर पॉइंट पे वैल्यू 1 आना चाहिए, उसकी वैल्यू 1 नहीं पता कैसे। तो इस तरीके से ए यूनियन ए कॉम्प्लीमेंट जो है इज ऑल्सो दैट इज नॉट ट्रू व्हिच इज ट्रू इन एस्पेक्ट सेट। तो दिस प्रॉपर्टी फेल इन फजी सेट से बिकॉज़ दिस जनरेशन जरूरी नहीं जितनी सेट होनी की प्रॉपर्टी हमने पहले आपके किस सेट के लिए प्रॉपर्टी आप यूज करें। इसी तरीके से इंटरसेक्शन में कॉम्प्लीमेंट इक्वल टू 0 जो प्रॉपर्टी ट्रू होती है एक्सेप्ट सेट एलिमेंट होती है और फजी सेट होगी दिस व्हाट हैज बीन इंडिकेटेड इन दिस प्रोपोजिशन लाइक ए इंटरसेक्शन इक्वल टू ए यूनियन इक्वल टू एंटिटी लॉस फॉर यूनियन इंटरसेक्शन yes to union intersection then the dispute law also this is also true in the fuzzy set intersection C. These are the properties of the fuzzy set, and then after that we have defined the concept of a fuzzy point. So, if you if you want to consider any point, singleton set. So, for studying singleton set, we will take the value 0 in all the points that is not equal to x0, and when x is equal to 0, we take its value as a real number greater than 0. So, the definition of a fuzzy point. Now, after this definition of fuzzy set, we come to the definition of how we define image and the image of a fuzzy set. Suppose capital A is fuzzy set and capital B is another fuzzy set. Now, whenever we want to define a fuzzy set, so we define a fuzzy set on any crisp set capital S. We take any function from the crisp set capital S to the closed interval 0, and that is our fuzzy set. So, whenever you want to consider any fuzzy set, you have to take a crisp set. Suppose capital A is a fuzzy set on crisp set capital S. And let us take another fuzzy set B on a crisp set. Means what is capital B? Capital B is a mapping from the crisp set Y to closed interval 0. So, now, suppose S is a mapping from set capital X to set capital Y. Now, here you see that capital X and capital Y, they are not sets, they are crisp sets. And that is a mapping from capital X to capital Y. That is our crisp mapping which we have already studied in school level. That S is a mapping from the set capital X to capital Y. That is a simply classical definition. Now, suppose I am mapping from the set capital X to capital Y, and A is a fuzzy set on capital X and B is a fuzzy set on capital Y. So, if B is a fuzzy set on capital Y, there is any image is denoted by S inverse B, and S inverse B is a fuzzy set on capital X. The definition is given in this. So, F inverse B is defined to be simply B of Fx. And the image of fuzzy sets f of A is defined by the formula supremum of A of S and 0. So these are the definitions. And then we come to the properties of the image and image of a fuzzy set. So these are very important. And basic properties of image and images of a fuzzy set, like the first property is here. And then we come to some more propositions, and now quickly come to the next topic. Yes. So after these, you can go through the properties, and they are given in. There are several books of fuzzy sets like Zimmerman and then Clear, and there are some more Indian authors are books are also available from Pragati University. And so from a student point of view, these books are very good for beginners. And after the properties, now I quickly come to the definition of fuzzy topological space. So the definition of fuzzy topological space, we define topological space. Suppose we take any set capital X, and then we take the collection of subsets of X, which we and we denote that family of collection of subsets of X by set of, and if that family satisfies some conditions, that first condition and to set phi and the whole set X belongs to that family of, and that family is closed under finite intersection, that family is closed under arbitrary union, then we topology, and X is a topological space with respect to the polygon. That is the definition of a topological space. So now, once analyze the split set two fuzzy sets, concept. And then after he has defined 1965. Then in 1919, somewhere 1968 or something like that, the concept of fuzzy topological space has I am not known, but so he has given the concept of fuzzy topology. So what is a fuzzy topology? Suppose capital X is an X set, and then again we take a family tau. Now this time tau is the family of fuzzy sets on X, and that family should satisfy against the properties. Now what is our empty set phi in the case of fuzzy set? That is the constant function 0. So the first condition is that the constant function 0 and the whole constant function 1 belongs to that family tau. Then that family tau is closed in a finite intersection. Finite intersection means suppose if I take any fuzzy set A in the family tau and if I take another fuzzy set B in the family tau, then A intersection B should belong to the family tau. And the third property is that tau is closed under arbitrary union. Means if I take arbitrary union of fuzzy set, now how we define the arbitrary union? Suppose the union of two fuzzy sets we define A union B to be simply maximum of AX of B. Now suppose there are infinite number of sets. Suppose A1, A2, A3 and dash dash. So the union of all these fuzzy sets AI, union AI is defined to be simply supremum of X belongs to capital X AIS. So the this family tau is closed under arbitrary union. Then we say that tau is a fuzzy topology on the set X, and capital X tau is called a fuzzy topological space. So in this way we have generalized this concept of topological space to in the category of fuzzy set, and we have defined the concept of fuzzy topological space. And after once we have defined the fuzzy topological space, then the members of the family tau are called fuzzy open sets. Their complements are called fuzzy closed sets, as we have defined in topological spaces. So after defining fuzzy open sets and fuzzy closed sets, we can define the interior of a fuzzy set and the closure of a fuzzy set. Suppose capital A is the fuzzy set, then what is the interior of a fuzzy set? So we take the union of all fuzzy open sets which are contained in A. Now how we define, suppose AX and BX are two fuzzy sets. When we say AX is a subset of BX, we say that AX is a subset of BX provided the membership function of AX is less than or equal to membership function BX for every small x belongs to capital X. Suppose capital X consists of say four elements x1, x2, x3, x4. And suppose our fuzzy set A, whose membership value is on x1 it takes value 0.1, on x2 it takes 0.2, on x3 it takes 0.3, on x4 it takes 0.4. And I take another fuzzy set B and it takes the membership function at x1 say 0.2, at x2 0.3, at x3 is 0.4, and x4 is 0.5. So we see that A of B because the membership value of A is less than the membership value of B. So in this way we find the fuzzy subset. So what is the definition of interior of a fuzzy set as we defined in topological spaces? Similarly, we can define fuzzy topological spaces. The interior of a fuzzy set is the union of all fuzzy open sets which are contained in it. And because arbitrary union of fuzzy open set is fuzzy open in the definition of fuzzy topological space, so the interior of a fuzzy set is a fuzzy open set. And what is a closure of a fuzzy set? The closure of a fuzzy set is the intersection of all fuzzy set, closed sets containing capital A. So the interior and the closure, and after defining the interior and closure of a fuzzy set, now we are after studying these concepts, you can enter in a very modern area of topology that is called fuzzy topology. As we defined in topological spaces, see we have in topological spaces we know what are open sets, what are closed sets. Now we can define now in topology there are several stupendous research has been done by defining the concept of semi-open set means generalized forms of open set like semi-open set, pre-open set, alpha open set, beta open set, and there are so many generalized forms of open sets were defined. So parallelly, these concepts were defined in fuzzy topological spaces, and using these generalized concepts of open sets, we find the generalized concept of continuity. The continuous map, in topological spaces, suppose X and Y are two topological spaces, and F is a mapping from topological space X to topological space Y. We say that F is a continuous map is the image of each open set in Y is open set in X. So similarly, suppose X dot is a topological space, Y dot X is another topological space, and F is a mapping from X to Y. We say that F is fuzzy continuous if the image of each fuzzy open set in Y is fuzzy open set in capital X. So that is the definition of fuzzy continuous map. Now, by replacing these open sets by the generalized open set, we suppose if I take any fuzzy open set in Y, and suppose this image I take to be open in X for defining continuity. But suppose I take the condition that the image of X open set is semi-open. Then this map is called semi-continuous. That is a generalization of continuous map because every open set is semi-open. But the semi-open set may not be open. So, in this way, we can generalize the concept of continuity by using semi-open set, pre-open set, alpha open set, beta open set. And once we have generalized the concept, several properties that some properties of topological spaces will hold here, some properties will not be hold. For that, we have to give the counter example. So that will there are tremendous research papers and research has been already done that very after defining topological as we have studied by topological spaces, means we take a set X and we take two topologies. Instead of single topology, suppose I take two topologies, tau1 and tau2, then X with two topologies are called by topological spaces. Similarly, if I take a set X and I take two fuzzy topologies, tau1 and tau2, then we have fuzzy bitopological spaces, and there are so many research work has also been done in this area also. So fuzzy topological spaces, fuzzy bitopological spaces, and there is a new concept also introduced in 2000 after 2002, I think. That is a concept of generalized fuzzy topological space. First generalized topology and then generalized fuzzy topological spaces, and then inclusive topological spaces. These are very new ideas, maybe in current time, and so I think this is a very little I have given to the students and Mr. Scholars, and who are interested in me, and I will give so I thank for giving me opportunity for giving for presenting my talk. Thank you, sir.